Mastering Ensemble Learning explained simply with demos. Ensemble Learning is a machine learning technique that combines the predictions from multiple individual models. They are called base or weak learners, and they're used to produce a single stronger prediction. The idea is that a group of these weak learners, which perform only slightly better than random guessing, can be unified into a single stronger learner with significantly better performance. The process generally involves training several individual learners and then using a combining module to aggregate their outputs into one result. Take homogeneous ensembles. All the base learners use the same learning algorithm. For example, random forest, which is an ensemble made up of only decision trees. Although each tree is trained on a different subset of data and considers different random subsets of features, the underlying algorithm for every single base learner is the same. In other words, a decision tree. Then you get heterogeneous ensembles. The base learners are built using different learning algorithms. A stacking module often uses a heterogeneous ensemble. For example, you could build an ensemble where the individual learners, in other words, the first level learners, are all different types of models. The ensemble might combine predictions from a support vector machine, a k-nearest neighbors model, and a naive Bayes classifier. In this example, you are combining three entirely different learning algorithms into a single predictive system. For an ensemble, in other words, the team, to be effective, there must be a situation where individual classifiers should be reasonably accurate, in other words, not bad, while also being diverse in their predictions, which contributes to higher overall accuracy. So, take for example boosting, which is a sequential machine learning method. There are several popular methods for creating effective ensembles. The main differences lie in how they are trained, or how they train their base learners and how they combine their predictions. So boosting is a family of algorithms that trains base learners, like I've mentioned, sequentially, and each subsequent model is trained to correct the mistakes of its predecessor. So how does it work? You start training the base learner on the initial dataset. After each training round, the algorithm adjusts the distribution of the training samples, giving more weight, importantly, to the instances that were incorrectly classified. Alright, so this forces the next learner to focus on the most difficult cases using a weighted dataset, and this process is repeated a t number of times, or number of rounds. So take this diagram for example. You'll see in the first row, or in the first column I should say, there are two incorrectly classified. And remember, it focuses on the incorrect, so it gives it a higher weighting in the second column, or the second iteration or second round. And the fourth classification in the second column was incorrect, so it gives it a higher weight applied to that. And it continues in the third one, and you'll see the ones that are incorrectly classified gets a, let's say, a larger vertical rectangle, which means more weight. Then you also get something called adaptive boosting, which is a popular boosting algorithm where the final prediction is a weighted sum of the predictions from all the base learners. The weights for each learner are determined by the accuracy, meaning more accurate learners get more higher weights. So it just means that there's different approaches. Alright, so you get a thing called bagging, a parallel ensemble method, also called bootstrap aggregation. Alright, it focuses on creating diversity among learners by training them on different subsets of the data. So how does this work? Bagging uses a technique called bootstrap sampling. For a dataset with n samples, a new dataset is created by randomly picking n amount of samples with replacement. What that means is you can pick it up from the sample, but once you're done, you put it back in. Alright, so that has a potential to create duplication because you have the opportunity to reselect the data from that data set, which adds some redundancy. So look at this example. You'll see in this example, records 2 and 5 was included in our sample data set, which we can see is like a duplication of some sorts. Alright, so this process is repeated t number of times to create T number of different training datasets, and a base learner is trained on each one. Thereafter, the final prediction is made by combining the outputs of all learners, typically through voting for classification tasks or averaging for regression tasks. So random forests, we've mentioned about diversity, it's a diversity booster. So think of random forests as an extension of bagging that adds another layer of randomness to further increase diversity, particularly for decision tree learners. Remember, bagging creates diversity by training each decision tree on a different bootstrap sample of the original data. In other words, it allows to look at all available features to find the very best one. Random forests does everything bagging does, plus it adds a second layer of randomness during the construction of each tree. In other words, think of it like feature columns at each split in addition to the data, so randomly selecting a small subset of features. So this additional randomness helps to decorrelate the individual trees, which generally leads to lower generalization error compared to bagging. Alright, so despite the added randomness, random forests are often more computationally efficient than bagging because each tree only needs to evaluate a small subset of features at each split, even though they involve an extra step of randomness. Alright, so ensemble learning, there's this concept of voting. So combining the outputs of base learners is a critical step. The choice of strategy depends on the task and the type of output from the learners. So you get voting for classification, and the types are of majority voting. A prediction is accepted only if more than half of the learners agree on it. Otherwise, it's rejected. You get plurality voting. The class label, think categorization of image to dog, cat, etc. receives the most votes is chosen as a final prediction. This is known as simple voting. Then you get weighted voting, where each learner's vote is multiplied by a weight, and the class with the highest total weighted votes wins. Alright, so we spoke about voting. You get hard and soft voting. Hard voting uses the predicted class labels directly. For example, the 0, 1, or ripe and unripe, or spam versus non-spam. Soft voting uses predicted class probabilities. In other words, a model's confidence scores for each possible class. For example, instead of a class label such as dog, cat, as I've mentioned, we have a probability value between 0 or 1, like cat. 0.7, which is a 70% confidence that it's a cat. Alright, so note, soft voting often performs better but requires well-calibrated probabilities from the base learners. In other words, reflecting the real-world likelihood of its prediction being correct. So you get averaging methods within ensemble learning. Averaging for regression, you get simple averaging. The final prediction is the simple average of the predictions from all individual learners, and you get weighted averaging. A weighted average is calculated where more reliable learners can be assigned higher weights. And then you get the concept of stacking ensemble learning using a meta learner. So how does it work? Stacking takes a different approach by using another machine learning model known as a meta learner to figure out the best way to combine the predictions. So step 1, the base learners or the first learners, think specialists, are trained on the original training set. For example, a random forest model, a support vector machine, a neural network. The second step, these predictions of these first level learners are then used to create a new dataset. In this new dataset, the predictions become the input features while the original labels are kept. Step 3, a second level learner. So you are training a new model on this new dataset to make a final prediction. So think of step 3 as a manager, which is our meta learning in this example, right? Think of multi-response linear regression, MLR. So data point transformation, you get the original data point. For example, feature A, feature B, and then the output or the prediction or the classification is cat. And then the meta learner, the new data point for the meta learner is the cat, dog classification, and it gives a prediction after that. So to avoid overfitting, the predictions used to train the meta learner must be generated on data that was not seen by the first level learners during their training. Example, by using cross-validation. So the success of an ensemble relies heavily on diversity, so this is quite crucial, amongst its base learners. If all the learners make the same errors, the ensemble won't improve upon the individual models. Therefore, diversity ensures that the errors of the learners are corrected by others. So there are 4 primary ways to generate diversity in ensemble learning. You get data sample manipulation, training learners on different subsets of data. And then you get input feature manipulation, training learners on different subsets of the input features. The random forest random feature selection is a key example of this. Then you get output representation manipulation, altering the class labels or output format to create different learning tasks for the base learners. And then you get algorithm parameter manipulation, using the same learning algorithm but with different parameter settings for each base learner to encourage different models. So what are typical examples of ensemble learning? Real-time transaction fraud detection. Think of a simple bank dashboard, web mobile app, and the user enters details for a new transaction. Example, the amount, the location, the vendor, and so on. So you have several simple models. A model that flags high-value transactions, a model that flags unusual locations, and a model that flags, for example, time of the day when the transaction was made. The ensemble prediction, for example, the bagging model combines these weak inputs to make a much more reliable prediction. Prediction approved for the transaction or prediction flagged for review. This is more accurate than any single rule. Let's look at another example. Student success early warning system. You have a dashboard for university lecturer department. Again, it shows a list of students in their modules. You feed the model data for the first few weeks of the term. Example, quiz 1 score, forum post count, login frequency, and then you have this ensemble prediction. The model combines again these weak predictors to flag a student as on track, they can continue, nothing to be alarmed about, or at risk. Then the lecturer can then intervene before the student fails, as an example. So let's look at a demonstration or two on the application of ensemble learning. In this ensemble learning demonstration, we'll be doing a simple homogeneous ensemble learning example. Python version using Windows operating system 3.14, pip is 25. If you want to create a virtual environment, depending on your environment, you can create one as such. All right, and then you activate it. And then you get started. So let's have a look at the code. So as you can see, the first step, we import the libraries. So the inputs are standard tools for math, data generation, data splitting, and the chosen model in this example is decision tree classifier. And you'll see something like this, a counter. Okay, the counter is to count the votes from all the different trees to see which prediction is the most popular. So we have the imports, and then we have the class, right? We're building a classifier. So in homogeneous ensemble, you may use many copies of the exact same type of algorithm, decision tree. In this case, like I've mentioned, a decision tree, and we do this to prevent them from all just learning the exact same thing. So you feed each copy a slightly different randomly shuffled version of the dataset. And this specific technique is called bagging, short for bootstrap aggregating. The basic bagging classifier is an implementation of the bagging bootstrap aggregation ensemble method. So here we're initializing the class parameters. The base learner is a single model that you want to copy. Example, a decision tree. Okay. And then here we're keeping our list. Eventually we'll populate or store the trained cloned models. Here we're getting the bootstrap samples or the sample data. This is the heart of bagging. So the bootstrapping means taking a data set and drawing a random sample from it with replacement. Okay. Let's make some sense about this. Imagine you have a hat with, say, 1,000 numbered tickets. You draw a ticket, you write down the number, and you put it back in the hat. You do this 1,000 times, you will end up with a list of 1,000 numbers. but some numbers will be picked multiple times and some will be left out entirely. So if we go to the fit, we fit the data to the model. We loop as many times we have models. Example, 100 times if we have 100 models. We create a brand new bootstrap dataset. We instantiate the fresh clone of our base model. We train that clone only on the bootstrap data and add the trained clone to our team roster, right? By the append. So once we've done that, we make a prediction. So every single model in our list makes a prediction for the test data. If we have 100 models and 300 test rows, we get 100 lists and each with 300 answers. Okay. So this flips our data grid. You see there? This is flipping our data grid. Instead of grouping by model, it groups by test sample. Now we have 300 lists and each list contains the 100 votes for that specific row. And then we do our predictions over here. We look at the votes for a single row. Example, class 1, class 2, class 1, and so on. The counter tallies them up, and the most common one found, whether it's class 1 or class 2, that's the winner. And 0 in brackets just extracts the actual winning label. Here we're implementing the classifier, right? So here we've been building it and loading the libraries. So now we are implementing it and we're creating a high dimensional data set. We create a data set with 20 features, 3 classes to be used. We generate fake synthetic data, right? Using make classification is synthetic data set that we're using. We are saying there are 5 columns that are just confusing copies of other data, and the classes means the models we have to choose between 3 possible answers instead of just, for example, 2 possible answers. Note regarding synthetic data, as I mentioned, this is synthetic data. Think of it in terms of mathematical algorithm being used to invent a data set that mimics the statistical properties of a real classification problem. In other words, think of synthetic data as creating a playground where you know exactly how many features are useful, informative, and how many are just noise, redundant. So why do we use synthetic data? Like in this example, we use synthetic data to benchmark models when real data is unavailable, restricted, or insufficient. If you are building a model as a prototype or proof of concept, you can use synthetic data to generate the idea before you start using real data. 20 features, 10 is informative, meaning they are useful, and I've mentioned 5, it's not useful, it's redundant. So let's look at the last part. This part, we are splitting the data into training and test sets. This part, we define the same unconstrained overfitting prone tree. So this part is crucial. By removing the depth limit, there we're saying have no depth to the decision tree traversal. Having no depth limit, the decision tree will grow endlessly until it has perfectly memorized the training data. So that perfectly is a keyword. This makes it highly unstable, meaning it's prone to severe overfitting. So if the data changes even slightly, this model's predictions will swing wildly. Right? Here we are training our base classifier. So here we are passing our unstable tree into the bagging classifier and ask for 100 clones. Thereby estimators, 100 model clones. Because of each of these 100 trees, the clones gets a slightly different bootstrap dataset. They all overfit in different ways. All right, so this one here, we just benchmarking against our ensemble model. Remember we said weak learners don't do so well. Combine them together, they cancel out each other's errors, so to say. All right, so we're using this for comparison to our bagging classifier. So let's run it and see what happens. It's doing the 100 decision tree bagging classifier, and there you can see the accuracy. It's higher than a single learner, base learner, weak learner. So if you were to update this to 500, meaning more of these learners, you click save and then you run it again, you will get a different output. As you can see, slightly improved, and you get the idea, right? So if we were to summarize this, the conclusion is that, as you can see, on high-dimensional data sets, the performance gap can be quite significant. And the reason for this is the single tree will perform poorly on the test set because it memorized the training data's noise, high variance. So the bagging classifier will perform much better, even though every single one of its 100 trees in this example, and then we change it to 500, is wildly overfitted. But because they are overfitted to different data, that's key. Included on the screen is an example of a single 10 lines of code scikit-learn version of a homogeneous ensemble method classifier. So you can have a look at that. For this ensemble learning demonstration, we're looking at heterogeneous ensemble learning. So once you're in your virtual environment, you want to import your libraries. Once you have them included, you would want to install it. So to install it, you would do pip install numpy. And because I have it installed, it will go fairly quickly, right? It's already installed. And if you want to install scikit-learn, right, it's already installed. So we don't need to carry on with that. So once everything is installed for you, right, remember ensemble is just a team of models working together. And a heterogeneous ensemble means that the team is made up of completely different types of algorithms, like putting, let's say, a biologist, a physicist, and a chemist in a room to solve a problem, right? So like I've mentioned, the first step, you import your libraries. Make classification, generate synthetic data. It's a random data set. It's perfect for testing algorithms without having to download real-world data. Voting classifier, this is the manager or the conductor of the ensemble. It doesn't learn on its own. It manages individual models and counts their votes. These three are distinct, diverse algorithms that we are inviting to our ensemble team, so to say. So now we have those. We want to load and split our data set. Here we want to create instances of different classifiers. In other words, the teams. Logistic regression. What can be said there? It's a statistical model that draws a mathematical line through the data to separate classes based on probability. So it's just a specific mathematical engine used under the hood with the solver of liblinear. Okay. All right. And lastly, SVC. This model tries to find the widest possible margin between different classes of data. By default, it makes a class prediction of 0 or 1. Okay, so then once we have the imports, we split our data, we create the instances of our different classifiers. Like I've mentioned, the team. Now what we want to do is we want to create the voting classifier. How are we going to choose the best classification? This is where we hand our three models over to the manager. We are creating a list of tuples, or it requires a list of tuples where we give each model a string, like DT for decision tree, and pass the actual model variable. Right, there's the model variables. Yeah, important thing, voting hard. We've touched on voting hard and soft. We can change this to soft if we're looking at average predicted probabilities. Remember, voting hard dictates how the final decision is made. Remember, hard voting, majority rules. If model A says cat, model B says dog, model C says cat, the ensemble predicts cat because 2 votes to 1. And soft voting, I've touched on briefly now. But soft voting, remember, it's average confidence. If voting was set to soft, the ensemble would look at how confident each model is, average out their probabilities, and pick the highest resulting average. Okay. So then lastly, we move over to training our ensemble, just like the other previous model. Right? We're fitting the data. The voting classifier takes the training data and feeds it to all three models individually. They each learn the patterns on their own unique way. This is self-explanatory. For every row, the decision tree, logistic regression, and SVC cast the individual votes, and the ensemble outputs the final majority decision. All right, so once we're done with that, we can run the model. You let that run. Are we not comparing it to a single classifier like we did with the homogeneous ensemble, which is doing the model and testing the accuracy? Okay, so I've also added an example of using real data from scikit-learn on the screen. You will notice that it does not look that much different from the synthetic data example demonstrated now. So using your own data won't be such a big leap.